So, one of the first practical asymmetric cryptography systems to be developed is RSA, named for the initials of the three co-inventors, Ron Rivest, Adi Shamir, and Leonard Adleman. This crypto system was patented in 1983 and was released to the public domain by RSA Security in the year 2000. The RSA system specifies mechanisms for generation and distribution of keys, along with encryption and decryption operation using these keys. We won't go into the details of the math involved, since it's pretty high-level stuff and beyond the scope of this class. But it's important to know that the key generation process depends on choosing two unique, random, and usually very large prime numbers. DSA, or Digital Signature Algorithm, is another example of an asymmetric encryption system, though it's used for signing and verifying data. It was patented in 1991 and is part of the US government's Federal Information Processing Standard. Similar to RSA, the specification covers the key generation process, along with the signing and verifying data using the key pairs. It's important to call out that the security of this system is dependent on choosing a random seed value that's incorporated into the signing process. If this value is leaked, or if it can be inferred if the prime number isn't truly random, then it's possible for an attacker to recover the private key. This actually happened in 2010 to Sony with their PlayStation 3 game console. It turns out they weren't ensuring this randomized value was changed for every signature. This resulted in a hacker group called Fail Overflow being able to recover the private key that Sony used to sign software for their platform. This allowed modders to write and sign custom software that was allowed to run on the otherwise very locked down console platform. This resulted in game piracy becoming a problem for Sony, as this facilitated the illicit copying and distribution of games, which caused significant losses in sales. I've included links to more about this in the next reading in case you want to dive deeper. Earlier, we talked about how asymmetric systems are commonly used as key exchange mechanisms to establish a shared secret that will be used with symmetric cipher. Another popular key exchange algorithm is DH, or Diffie-Hellman, named for the co-inventors. Let's walk through how the DH key exchange algorithm works. Let's assume we have two people who'd like to communicate over an unsecured channel, and let's call them Suzanne and Daryl. I've grown pretty fond of these two. First, Suzanne and Daryl agree on a starting number that would be random and will be a very large integer. This number should be different for every session and doesn't need to be secret. Next, each person chooses another randomized large number, but this one is kept secret. Then, they combine their shared number with their respective secret number and send the resulting mix to each other. Next, each person combines their secret number with the combined value they received from the previous step. The result is a new value that's the same on both sides without disclosing enough information to any potential eavesdroppers to figure out the shared secret. This algorithm was designed solely for key exchange, though there have been efforts to adapt it for encryption purposes. It's even been used as part of a PKI system, or public key infrastructure system. We'll dive more into PKI systems later in this course. Elliptic curve cryptography, or ECC, is a public key encryption system that uses the algebraic structure of elliptic curves over finite fields to generate secure keys. What does that even mean? Well, traditional public key systems make use of factoring large prime numbers, whereas ECC makes use of elliptic curves. An elliptic curve is composed of a set of coordinates that fit an equation, similar to something like y to the second equals x to the third plus ax plus b. Elliptic curves have a couple interesting and unique properties. One is horizontal symmetry, which means that at any point in the curve can be mirrored along the x-axis and still make up the same curve. On top of this, any non-vertical line will intersect the curve in 3 places at most. It's this last property that allows elliptic curves to be used in encryption. The benefit of elliptic curve-based encryption systems is that they're able to achieve security similar to traditional public key systems with smaller key sizes. So, for example, a 256-bit elliptic curve key would be comparable to a 3072-bit RSA key. This is really beneficial since it reduces the amount of data needed to be stored and transmitted when dealing with keys. Both Diffie-Hellman and DSA have elliptic curve variants, referred to as ECDH and ECDSA, respectively. The US NIST recommends the use of EC encryption, and the NSA allows its use to protect up to top secret data with 384-bit EC keys. But the NSA has expressed concern about EC encryption being potentially vulnerable to quantum computing attacks, as quantum computing technology continues to evolve and mature. I'm going to buy Suzanne and Daryl a drink today for all their hard work. In the meantime, we've cooked up an assignment for you that will test your encryption and decryption skills. Take your time to decode all the details, and I'll see you all in the next lesson.